right, hi everyone. We are going to finish up some of the 5.5 notes on using rational functions equations to determine information about their graphs and then practice graphing some of these. So bear with me because I can't pause. Well, I could pause recording, but I'm going to try my best to make this a solid process. Don't quote me on that. Okay, so where we left off, at least in one of my classes, and if your class went ahead beyond this, just fast forward to where we left off. But right here at example 3 of the asymptotes of a rational function. So just to recap what we talked about, we have vertical asymptotes, which are determined by those restrictions, and we have those two different cases. So we have those essential discontinuities that result in vertical asymptotes, and we have the removable discontinuities which result in the holes in the graph. So that's just what we've already talked about. Then we talked briefly about horizontal asymptotes. So those are the asymptotes that a function might approach, and they always determine end behavior. So for example, something like that, we can figure out the equation of that horizontal asymptote in two ways. The first way is if your numerator degree is less than the denominator, then this is always going to approach 0. A number is always being divided by an infinitely larger number as x gets bigger and bigger. So that would be a horizontal asymptote of 0, something getting closer and closer to the x-axis. Otherwise, if they're the same, fourth degree here, the asymptote is given by that ratio of coefficients. So in this case, the horizontal asymptote would be 10/3, which is just slightly over 3. So 1, 2, 3 would be slightly over that. And whatever that function did, it would approach 3 at the end behavior, or 10/3 at that end behavior. Okay, and so then with the oblique asymptotes, that happens when you've got oblique, remember, is just like a linear or diagonal. It's not horizontal or vertical, it's linear. So a slope other than 0 or no slope. So that happens when, and this should make sense, when your degree of your numerator is 1 higher than that degree of the denominator. So when you divide something of a second power by something to the first, that quotient is of degree 1, which is linear. So that's where we left off in class. Okay, so I paused for a second here to pull up the graph of this function right here to show you an oblique asymptote. So I graphed this, I've just entered it into the y equals, I'm looking at the graph, and then from class, what we did was actually find the quotient when x squared minus 5x minus 6 is divided by x plus 2. I used synthetic division to get the quotient, which is the equation of my oblique asymptote. So when I go back here, and I'm going to graph the oblique asymptote along with this function, so x minus 7, and when I graph it, we'll see that the function approaches that asymptote. So we can see it growing closer and closer to our blue function, and even if I zoom out a little bit here, we can see long-term the end behavior of this function is going to approach the line y equals x minus 7. So that oblique asymptote, just to kind of show you how that helps us figure out end behavior there. All right, so next we have other asymptotes. We had our situations, lower degree in the numerator, same degree, 1 degree higher, or more than 1 degree higher. And it follows the same rule or process as the oblique asymptotes. You get the quotient, and the equation of the quotient is the asymptote, and it's not always going to be linear. So if it's not linear, like in this case, we have a 4th degree polynomial divided by a 2nd degree polynomial, and the quotient, when I do the division for this, which is long division, will be the equation of the oblique asymptote. Okay, so what I just did was pause to type in this equation into my y equals, and hopefully you guys can see this graph okay. So I just typed it in. I tweaked my window range a little bit to get a wider view of this graph, which is really interesting. And now I did the long division here. This quotient is the equation of the asymptote. And this quotient, if you see here, is degree 2. So I actually have a parabolic asymptote, or an asymptote that's in the shape of a parabola. So I'm going to pause here and type that in and show you what it looks like on the same graph. Okay, so I paused here to type in the equation of the quotient, which is 3x squared plus 2x minus 18. I made a mistake there. That's not 18x. So I type that in and look what happens on the graph. So we see the red parabola. That's my asymptote. It's okay for that to overlap with this piece of the function. What is important about asymptotes here, even this parabolic one, is that the inside pieces of my function, the blue ones, which is my actual function, are always within the bounds of this asymptote. So they will always approach whatever the asymptote is approaching. So I just wanted to show you guys some of these more unique asymptotes that you guys might come across. All right, so let's move on to another bit of review, but worth taking the time. And that is x-intercepts and y-intercepts. And then we're going to put all of this together and get as much information about a rational function as we can from the equation itself, not from the graph. So x-intercepts, hopefully a good review, but worth mentioning. X-intercepts, this is my x-axis. The key for finding x-intercepts is think about what the y value equals on the x-axis. The y value always equals 0 right here. So to find the x-intercepts, all you do is set the whole thing equal to 0, set y equal to 0, and solve for x. So those are always your x-intercepts. For y-intercepts, it's the reverse of that. Anytime a function crosses the y-axis, think about what its x value is. It would be 0. So for the y-intercept, you plug 0 in for x and solve for y. So we'll work through this example together really fast. So here's my function. It's already been factored. Let's look at the x-intercepts first. So again, anytime this function crosses the x-axis, the y value is 0. So basically I'm setting this equal to 0. And a fraction equals 0 anytime the numerator equals 0. So really I just care about when x plus 4 times x minus 2 times x plus 1 equals 0. In this case, because I have these common factors in the numerator and denominator, -4 is not actually an x-intercept. -4 is a restriction since x plus 4 also appears in the denominator. So my x-intercept is coming only from where x minus 2 times x plus 1 equals 0, which would be 2 and -1. So these are my x-intercepts. So if we wanted, I could write those as points, 2, 0, and -1, 0. My y-intercept, remember y-intercepts happen when x equals 0. This is nice because we're literally just plugging 0 in for x. So when I plug 0 in for x, it doesn't matter if you take the x plus 4s out or not. Those two values, 4 over 4, are going to cancel out anyways. So I always just stick with whatever's left after I reduce. So this would be 0 minus 2, so -2 times 1 divided by -3. So I've plugged 0 in here, here, and here. And I get -2 over -3, which is 2/3. So 2/3 is the y-intercept. 0, 2/3. So these are my x and y intercepts. All right, so let's put this all together. So when I give you guys a rational function, I am going to expect you to tell me all this information without even graphing it. So don't jump to graphing because we want to piece as much of this graph together on our own, and then we'll fill in the missing spaces with a calculator. So first I'm going to look at this and look for discontinuities, what kind of discontinuities and where they occur. So I'm looking at this and I know I have a restriction. X cannot equal 4 here, which means 4 is a discontinuity. X equals 4, and I need to think about what kind. So since x minus 4 doesn't cancel here with anything in the numerator, this is an essential discontinuity, which we know is going to result in a vertical asymptote. So here I can go ahead and even jump down to this vertical asymptote or equation of asymptotes because I know I'm going to have a vertical one at x equals 0. Similarly, my horizontal asymptote, remember that's coming from the leading coefficients and whatever their powers are. So what I'm going to end up with here is a cubic function, 1, 2, 3. So if I distribute it, divided by a linear function, that's going to result in a second degree asymptote. You do not need to worry about putting equations of those asymptotes here. So when I ask for equations of asymptotes, I'm going to focus on horizontal and vertical. Just FYI. Okay, so what can I do right now? I can at least plot an asymptote right here at x equals 4. And then I'm going to move on to my x-intercepts and y-intercepts. All right, x-intercepts. Remember, I'm setting the whole numerator equal to 0. Well, if I set that equal to 0, and you don't necessarily need to write out all of these steps, then I would get x equals 5, x equals -3, and x equals -1. 5, -3, and -1. And I can plot those too. A point at 5, -1, and -3. So I know my function is going to hit my x-axis there. I've got this, and the last thing I can find here is the y-intercept, which remember I'm plugging 0 in for x. So that's going to be 0 in for x here. So f of 0, that's going to be -5 times 3 times 1 divided by -4. So I've got in the numerator -5 times 3 times 1, -15 divided by -4. So that's going to end up being a positive, and 15/4 is 3.75. So that's my y-intercept. So a quick sketch of what I have. So these are the 4 points I have on my graph and the asymptote. I don't know what exactly this is going to do, because this is interesting to have these 2 points here, a third point there, and one over on this side of the asymptote. So I've done everything I can to piece together what this function is going to look like. Now that we have a kind of starting point, like the outline of this function, now we can use our calculator to figure out what it's actually going to look like. So to type this in, just be careful, because you do have these 3 sets of parentheses up here, so you're going to need to put parentheses on all 3 of those. So we've got x minus 5 times x plus 3 times x plus 1, and parentheses divided by x minus 4. And I'm going to go back to my standard viewing window here, and let's see if this lines up with what we've got. Okay, so these 3 points right here, this makes sense. This is our parabola. So there's 2 pieces of this function. On the left side of my vertical asymptote, we've got a parabola. So I'm going to sketch that in. On the other side of the vertical asymptote, we've got this funky line. It's not actually a line, it is a curve. And if we zoom out, we can see that a little bit better. It is just kind of slowly curving up, but not vertical, even though it looks like it. So we found out a lot of information before we even looked at this graph. And that's what we're going to continue doing on some of these other examples. So moving on to example 5, I've got another factored form, x minus 5, x plus 3, x plus 1 over x plus 3. So again, first we're going to look at asymptotes, discontinuities, intercepts, and then piece together as much of this graph as we can. I have a discontinuity here. The good thing is it cancels out with the numerator. So this is actually a removable discontinuity. In other words, a hole at x equals -3. And what if I want to know the actual point? A removable discontinuity is a hole which has a coordinate. So if x was 3, that's going to be the y coordinate of this hole. So 3 comma, so I would plug 3 in after you make that cancellation. So it would just be x minus 5 times x plus 1. So that would be -2 times 4. So I have this discontinuity at, oops, I'm plugging in -3, hold on. So -3 minus 5, sorry about that, is -8. And -3 plus 1 is -2. So we've got a hole at -316. 1 second. Okay, next to find the x-intercepts. Remember, I'm just setting the numerator equal to 0. I'm not going to include the x plus 3 because I don't have a 0 at -3. I have a whole at -3. So it's not going to be one of the zeros. So the only two x-intercepts I have come from when x minus 5 equals 0, which would be at +5, and when x plus 1 equals 0, which would be at -1. So I'm going to start building this. I've got an x-intercept at -1. 1, 2, 3, 4, +5. And then let's get my y-intercept. That's going to be when I plug 0 in for x, which would give me, and again, I can include the x plus 3s here. They're going to cancel either way, so I just usually ignore them. So that would be -5 times 1. So I've got a y-intercept at -5. So 1, 2, 3, 4, 5. Okay. So this is all I've got right now. I also know I have a whole at -316, which is going to be way down off of my graph. Wait, -3, actually, -316 up here, way off of my graph up here. All right, so let's think about what this is going to be. I have a degree 3 numerator, degree 1 denominator. So that should simplify. So when I go to my y equals, I've typed this in already. Let's see how we're going to piece the rest of our graph together. So plug it in, graph it. And this ends up being a parabola. So I'm looking, just match it up, make sure these points are making sense. And then I would sketch in the graph according to my calculator. So we've got a parabola there. The interesting thing on this one too is since we know there's a hole at -316, I can hit the trace button and actually type in -3. There is a hole on this graph. So when I type in -3 for x, I should not expect an output. So we see there is no output for y here because there's a hole there from this denominator of x plus 3. All right, so let's move on to the next page. Okay, so I'm going to move on here to problem 6 and then probably stop with this. I think this would be enough for you to complete the 5-5 homework sheet. So again, we've got this equation in factored form already. So that's helpful in determining the discontinuities and the intercepts. So the type of discontinuities I see, remember discontinuities come from the denominator. Here I have something that cannot equal -3 and it cannot equal 4. Those would be our restrictions. And now we're going to figure out what type of discontinuities they are. Looking at my equation, I see x plus 3 in both numerator and denominator. So I've got a removable discontinuity at x equals -3. And I've got an essential discontinuity when x equals 4. In other words, this essential discontinuity of x equals 4, that is definitely the equation of my vertical asymptote, x equals 4. So right away, that's not very good. Okay. I can put this here. All right. The removable means I've got a hole at -3. So if I want to know the coordinates of that hole, I would evaluate my function when x is -3 when I remove these two factors here. So f of -3 would be -3 minus 8, or -3 minus 5, so -8, -3 plus 1, -2, which is +16. And then -3 minus 4, which is -7. So I've got a hole here at -16 over -7. So let's get a decimal, about -2.29. So that'll be helpful when I'm piecing my graph together. So, okay, x-intercepts. That is when my numerator equals 0, but I'm not including this -3 because remember, that's where my hole is. So my x-intercepts are 5 and -1, very similar to my last equation. If you've noticed, maybe you haven't, by the way, from this last problem we did, these equations are almost identical. The only change, I'll show you really fast, is that my denominator I've added x minus 4 to this denominator, and we're going to see how that changes this function. So it introduced a vertical asymptote, but I still had the same points, -1 and 5. It also changed where my hole is, and now I can get my y-intercept, and it will change that as well. So remember, y-intercepts come from where I plug 0 in for x, so f of 0. So that would be -5 times -1 divided by -4. So 5/4, which is 1.25. So it's right there. Okay, so there's my x-intercept. Or that's -1.25. Positive 1.25. Okay, so this is not going to look like the last graph we did. This is definitely different. I'm going to enter that into my calculator and see if I can fill in the gaps after we've done everything that we can by hand. So type that into your calculator. I'm going to pause the recording here. Okay, so I've typed this into my calculator in the y equals. Make sure you've entered it in correctly. Include all pieces, especially these x plus 3s. Some people ask, can I just leave that out when I type it in? We don't want to leave it out because we want the original function, how it was. So when I look at my function now, I've got that piece and that piece. Okay, so what's not shown in here is this vertical asymptote at x equals 4. So these 2 points right here are being connected by this curve that kind of looks linear, and then it starts heading up towards infinity. It starts increasing much more quickly. And then this curve over here, which is similar, it looks like it's pretty vertical, and then it actually starts to head over to the right. So this is the graph that would produce after we piece together these discontinuities and intercepts. Okay, so I'm gonna stop here because we've covered the bulk of this stuff. So this looks like a really long section. If you keep looking through the next few pages, you just see several pages, but that's because I only put a couple of examples on each page. I will stop here for now. You should be able to get through a lot of your 5-5 homework, and we can visit any questions you guys have on that in class. Okie doke, see you soon.